Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, stop me if you've heard this one before. A mysterious object from, a totally different star system just waltzes into our solar system. It's weird, it's moving impossibly fast, and it's basically carrying secrets from some alien world. And then, just as we figure out what it is...
poof, it's gone.
It's gone, it's already on its way out.
It really does feel like a recurring theme, doesn't it? It's the cosmic equivalent of meeting someone fascinating at an airport, having a great conversation, and then their flight gets called.
It's the ultimate cosmic tease. We're sitting here. It is February 16th, 2026, and the entire astronomy world is buzzing about this thing. 3I Atlas.
Yeah, the third one.
This is it, the third interstellar object humanity has ever detected. First, we had Oumuamua back in, 2017, that weird tumbling cigar-shaped thing.
That caused so much debate.
Then Borisov came along a couple years later, and it looked a little more familiar, a bit more like a normal comet.
A bit, yeah.
And now, ATLAS. But the headline feels exactly the same. Hello, goodbye, nice knowing you.
It's just so frustrating. I mean, the geometry of these encounters it's just unforgiving. By the time our telescopes are powerful enough to spot them, they are usually already screaming past the sun and heading for the exit door.
Right.
The universe is like throwing these incredible gifts at us, but it's throwing them really, really hard.
Exactly. And the mood today, you can feel it online. It feels a bit somber, right? Like we missed the bus again. I was just looking at the trajectory maps this morning, tracking it on the NASA dashboard. And 3I Atlas is moving at something like 60 kilometers per second.
60, yeah.
That's not just fast. That is, don't even bother trying to chase me fast.
Well, under normal circumstances, yes.
Yes.
That is exactly what the physics would tell you. 60 kilometers per second it's blisteringly fast.
Put that in perspective for us.
Okay, so a high-velocity rifle bullet travels at about 1 kilometer per second, give or take.
Oh. Well.
So this rock is moving 60 times faster than a speeding bullet. It's completely unbound from the sun's gravity, which means it isn't coming back. It's a one-time visitor, a true interstellar tourist.
The cosmic drive-by.
Precisely.
Right.
And usually when something is moving that fast and is already on its way out, we wave. We take our telescope pictures, we analyze the light spectrum from afar, and we write our papers about the one that got away.
But, I hear a but in your voice.
But, and this is why today is actually a very, very exciting day.
Mm-hmm.
The entire narrative has just shifted in the last few hours.
Shifted how? The thing is leaving. It's got to be halfway to Jupiter's orbit by now, isn't it?
It is leaving, and you're right, we absolutely can't catch it with a normal chase. A direct shot is impossible. But a new proposal just dropped today that suggests we actually can catch it.
You're kidding.
It's just that the method is, it's completely unhinged.
Unhinged. I like unhinged. Unhinged usually means interesting.
Oh, it's audacious. It's beautiful. The proposal comes from a team, including Adam Hibbard, who's with the Initiative for Interstellar Studies. They've crunched the numbers, and they are saying we can run this object down, but we don't do it by flying towards it.
Okay. I'm listening. Where do we fly then?
We catch it by flying directly into the sun.
I'm sorry, what? Come again.
Yep.
We want to catch a freezing cold rock that's heading out into the blackness of deep space, and step one of the plan is fly into the giant ball of fire.
Step one is fly into the fire. It's a technique called a Solar Oberth maneuver, and if this paper is right, it is the only way humanity is going to get a close-up look at an alien object in our lifetimes.
Okay, we have to unpack this immediately, because that sounds like suicide, not science. But hold on, before we even get to the whole flying into the sun part, we need to set the stage properly. What exactly is 3I Atlas? Why are we so desperate to catch this thing that we're seriously considering roasting a multi-billion-dollar spacecraft?
Well, you have to think about what these objects really represent. 3I Atlas isn't just a rock or, a dirty snowball. It's debris. It's leftover building material from the formation of a completely different solar system.
It's literally a message in a bottle.
Precisely. It's a physical package containing the chemical history of an exoplanet system. We spend billions and billions of dollars building these incredible telescopes like Webb to just stare at the atmospheres of planets light years away, trying to guess what they're made of from these tiny squiggles in a light spectrum.
Right, it's all remote analysis.
But here, the universe has literally mailed a piece of one to our front door. If we could actually sample it, touch it, put it in a mass spectrometer, and analyze its isotopes,
yeah,
my God, it would be the scientific gold mine of the century.
It would tell us if our own solar system is, like, unique or if we're just...
Common? Are we common or are we a fluke? That's one of the biggest questions there is.
Right. It's the difference between looking at a picture of a cake and actually getting to eat a slice. But here's the problem, and this is what everyone is lamenting today. We can't eat the slice because the slice is moving at 60 kilometers per second away from us.
And that speed is the whole key to the problem. To put that 60 number in perspective again, the fastest spacecraft we've ever launched out of the solar system is Voyager 1.
And it's been going for what, almost 50 years now?
Almost 50 years. And it's moving at about 17 kilometers per second. 17. And that took decades of gravity assist to build up. 3i Atlas is moving more than 3, almost 4 times faster than our fastest ever probe. We just can't catch it conventionally.
So why can't we just, I mean, this is the obvious question, right? Why can't we just launch a bigger rocket? We have these huge new rockets, the SLS, we've got Starship. Can't we just strap a probe to one of those and just floor it?
That's the direct mission approach?
Yeah.
It's a totally logical question, and it's the first thing every mission designer looks at. But the math, it just falls apart almost immediately. The issue isn't just the sheer speed, it's the timing. It's a combination problem. 3i Atlas was detected far too late in the game. It had already crossed inside Jupiter's orbit and swung around the sun before we even knew it was there.
It totally snuck up on us.
It really did. And because it was detected so late, the optimal launch window, that perfect time when Earth was in just the right spot in its orbit to simply shoot a rocket to intercept it, that window had already slammed shut. It was gone before we even knew it existed.
It's like trying to merge onto a highway. If you see a car coming from way down the on-ramp, you can time it, you speed up, you merge in smoothly.
Perfect analogy.
But if that car has already blown past you while you're at a dead stop, you can't just accelerate from 0 to 100 miles an hour instantly to catch up. The physics doesn't work.
You're standing on the train platform, and the bullet train has already screamed past the station. That's the situation we're in.
Okay, but what if we were already in space? I know the European Space Agency has this mission planned, the Comet Interceptor. The idea is to have a probe just kind of waiting, right?
Loitering, yeah. The concept is to park a spacecraft at a stable point in space, the Sun-Earth L2 point, and just wait for a suitable long-period comet, or, ideally, an interstellar object to show up.
So even if we had one of those waiting right now, it wouldn't work?
It wouldn't matter. The angle is all wrong, and the speed is just too high. The sheer change in velocity required, we call delta V in orbital mechanics, is just monumentally beyond the capability of any chemical rockets we have sitting on a pad or even waiting in space.
So delta V is basically a measure of how much oomph you need.
It's the currency of space travel. Every maneuver costs a certain amount of delta V. Getting from Earth orbit to the moon costs a certain amount. Getting to Mars costs more. Trying to catch 3 Aiellas from a standing start costs an astronomical amount. If you tried to pack enough fuel to do it, you'd need a rocket the size of a skyscraper just to get a tiny coffee cup-sized probe moving fast enough. And we can't build that.
So the direct approach is dead on arrival. Conventional wisdom says we wave goodbye, write some sad poetry, and wait for the next one in, another couple of years?
That was the conventional wisdom until this morning.
Okay, so enter the visionaries. Who are these people proposing the dive into the sun plan? This sounds like a pretty maverick idea.
It is, but they're not mavericks in a reckless sense. It's a fascinating team. You have Adam Hibbard, who is just a brilliant orbital mechanic from the Initiative for Interstellar Studies, or I4.
Okay.
Then you have T. Marshall Eubanks from Space Initiatives, Inc., and Andreas Hein at the University of Luxembourg. These aren't just random enthusiasts. These are the folks who specialize in impossible navigation. They live for these kinds of problems.
They like the hard problems.
They love them. And Hibbard, in particular, is the main architect behind a really unique piece of software called OITs.
OITs? What's that?
It stands for Optimum Interplanetary Trajectory Software. It sounds dry, I know, but you should think of it as a kind of GPS for the impossible.
How so?
Most mission planning software is designed to look for the most efficient direct routes. A Hohmann transfer from Earth to Mars. It's about saving fuel on established paths. OAS's is different. It's designed to look for cosmic bank shots. It looks for gravitational pinball.
So it's not looking for the straightest line, it's looking for loopholes.
It's looking for leverage points in the solar system. And this isn't its first rodeo. It was the same software used to design Project Lyra, which was the big theoretical mission concept to go back and chase down Oumuamua.
Oh, I remember that. That also seemed impossible at the time.
It did, and a direct mission was. But always found these wild looping trajectories using Venus and Jupiter and Earth to eventually build up enough speed. So this software has a pedigree in solving these exact kinds of impossible navigation riddles.
Okay, so these guys fed all the data on 3IA Plus, its speed, its direction, into this super smart software, and just asked it a simple question.
A very simple question. Is there any way at all, using any combination of planets and burns, to catch this thing with current technology?
And the computer didn't just crash.
The computer came back with a resounding yes. But the path it plotted, it's just wild. It's elegant and terrifying all at once.
Which brings us back to the Solar Oberth maneuver.
The Solar Oberth.
Okay, lay it on me. I think I understand a basic gravity assist. That's where you fly by a planet like Jupiter and you kind of steal a little bit of its orbital momentum to speed yourself up, right? Voyager did that a bunch of times.
Exactly right. A standard gravity assist is like you're on a skateboard and you grab onto the back of a moving bus for a second. The bus barely notices, but you get a huge boost.
Right.
But the Oberth effect is different. It's more profound. It relies on a quirk of orbital mechanics that almost feels like a cheat code for the universe.
A cheat code? I'm listening. I like cheat codes.
The basic principle is this. A rocket engine is more efficient. It gives you a bigger boost in kinetic energy when the rocket is already moving very fast.
Wait, hang on. Why? That seems backwards. A rocket provides a certain amount of thrust, a certain push. Why does it matter how fast I'm already going when I fire it?
It's all about kinetic energy. The formula for kinetic energy is 1/2 mass times velocity squared. The key is that squared part.
Okay.
So because of that squared relationship, if you add a fixed amount of velocity, let's say you fire your engine and add 1 kilometer per second to your speed, the amount of energy you gain from that burn is massively larger if you're already going, say, 50 kilometers per second than if you're only going 5. You get more bang for your buck from the exact same puff of gas.
Okay, I think I'm starting to get it. So you want to save your biggest engine burn for the moment you're moving at your absolute maximum speed.
Precisely. That is the key to the whole thing. So the next question is obvious. Where in our solar system does an object move the fastest?
When it's falling towards something really, really heavy.
The sun. The sun is the biggest, deepest gravity well we have by a long, long shot. If you just drop a spacecraft and let it fall towards the sun, gravity pulls it in, accelerating it faster and faster and faster.
It's like rolling down the universe's biggest hill.
Exactly. By the time it gets really close to the surface, or, well, the photosphere, it is just screaming. It's moving faster than any man-made object has ever moved in history.
So you let the sun do all the hard work of acceleration for you.
You let gravity do the heavy lifting. You dive. You fall all the way down into the deepest part of the well. And right at the very bottom of that dive, the point called perihelion, the closest point to the sun, you are moving at these incredible mind-bending speeds. And that is when you fire your engine.
You hit the gas at the very bottom of the hill.
That's it. It's like being on a swing set. If you try to pump your legs at the very top of the arc, when you're almost motionless, it doesn't do much.
Right, you just kind of wiggle.
But if you give a huge kick right at the very bottom of the swing, when you're moving fastest, you go flying so much higher on the other side. This is the ultimate cosmic swing set. You dive at the sun, and at that single precise moment of closest approach, you burn everything you have. The combination of the sun's intense gravity and that perfectly timed rocket burn flings you out of the solar system like a stone from a god's slingshot.
That is terrifyingly brilliant. So we're not really chasing 3I Lace at all. We're using the sun to catapult ourselves onto a trajectory that will eventually intercept it way out in deep space.
Yes, we're setting an ambush. The math in this new paper suggests that this maneuver can generate the kinds of exit speeds we need, well over 60, maybe 70, even 80 kilometers per second, to actually run down an interstellar object that had a massive head start.
But there's a catch, right? There's always a catch. This sounds too perfect. You can't just launch this mission tomorrow.
No. Absolutely not. And this is where the beautiful, frustrating reality of celestial mechanics comes back in. It's a game of alignment. You need the planets to be in exactly the right places, literally. For this to work, we need Earth, Jupiter, and the Sun to be in very specific positions relative to 3ILS's escape path.
Okay, wait, why Jupiter? You lost me there. I thought this was all about the sun.
It is, but we can't just fly from Earth to the sun directly. It's actually, and this sounds crazy, it's really hard to hit the sun.
It's the biggest thing around. How can it be hard to hit?
Because the Earth isn't stationary. We're moving sideways at about 30 kilometers per second in our orbit. To fall into the sun, you first have to get rid of all that sideways momentum. It takes a huge amount of braking fuel. So the clever plan is this. Launch from Earth and first fly out to Jupiter.
So you go outwards to go inwards? That makes no sense.
It's the bank shot.
Yeah.
We use Jupiter's massive gravity not to speed up, but to slam on the brakes. We do a gravity assist in reverse. It cues our orbital speed, turns the spacecraft around, and drops it into a dead dive, straight at the sun.
Wow. So the full itinerary is launch from Earth, fly out to Jupiter for a few years, use Jupiter to U-turn and dive into the sun, do the crazy Oberth run, and then shoot out into the void to chase ATLAs.
A bank shot off the king of planets into the heart of the star to catch a ghost.
So according to Hibbert and his team, when does this magical cosmic window open? When are all the pieces in the right place?
2035.
2035. Okay, so that's 9 years from now.
9 years, which in the world of designing and building major flagship space missions is actually a very comfortable timeline. It's not a frantic scramble. It's doable. We could do this.
But let's talk about the tech for a minute, because usually when I hear people talk about chasing interstellar objects, they immediately start talking about, laser arrays and light sails and antimatter engines, stuff that belongs in Star Trek. Is that what this requires?
No. And that is probably the most important and exciting part of this new proposal. They are not asking for science fiction. They're not asking for directed energy propulsion or giant laser arrays on the dark side of the moon.
Which is cool, but decades away.
Decades away at best, yeah. This proposal is based on using solid rocket motors, chemical propulsion, the same fundamental stuff we've been using to launch satellites since the 1960s.
You're kidding me, just standard rockets. How can that possibly be powerful enough?
Well, specialized, of course. You need a kick stage that can survive the heat. But the physics of the Solar Oberth maneuver are so powerful that they compensate for the relative weakness of our chemical fuel. We don't need a sci-fi engine, because we are using the sun itself as our primary engine. The physics gives us the leverage our chemistry lacks.
That makes it feel incredibly real. This isn't some maybe in 100 years academic paper. This is we could start bending metal for this tomorrow kind of paper.
It is. The technological readiness level, or TRL, for all the key components is very high. We know how to build heat shields. We did it with the Parker Solar Probe, which is practically touching the sun's atmosphere right now and surviving.
Right. Parker's a huge success.
We absolutely know how to do Jupiter flybys. We've been doing them since the Pioneer missions in the 70s. And we definitely know how to make reliable, solid rocket motors. The pieces are all on the board. We just need to assemble them in this new, audacious way.
Okay, so we have the target, 3I-8-less. We have the mind-bending method, the Solar Oberth. We have the technology. It's basically off the shelf. But now we have to talk about the elephant in the room. Or maybe the tortoise in the room.
The duration.
The duration, because I saw the number in the abstract of the paper and I had to read it twice to make sure it wasn't a typo.
How long does it actually take for this probe after its 2035 launch and solar dive to catch up to 3I-8-less?
The baseline simulation suggests a flight time of approximately 50 years.
50 years.
No, that's a century.
So let me get this straight. We launch in 2035. The probe performs its dive, gets flung out into space, and it finally catches the object in 2085.
That's the timeline, yes.
I mean, most of the people working on the mission, the engineers, the scientists who build it, they won't be alive when it arrives. That is very likely true, yes.
Wow, that is a hard sell, isn't it? Hey, Congress, can you give us a few $1 billion for a mission that will give us some really cool photos for our grandkids in the year 2085?
It's a hard sell if you look at it through the lens of, typical 4-year election cycles or quarterly corporate reports. But this is where we have to fundamentally shift our thinking. This isn't a normal mission. We have to move into the realm of what some people call cathedral projects.
Cathedral projects, explain that.
Think about the architects and the stonemasons who laid the cornerstones of the great cathedrals in medieval Europe. They knew with absolute 100% certainty that they would not live to see the spire completed. Their children might not, their grandchildren might not even see it finished, but they started anyway.
They were building it for the future, for something bigger than themselves.
They were building it for the future. This mission is a scientific cathedral. It's a legacy project.
That is a beautiful way to put it. But practically speaking, can we even maintain a mission for 50 years? I mean, equipment breaks. Radioactive power sources decay. Signals degrade over those insane distances.
We have precedent, and it's an amazing one. Voyager 1 and Voyager 2 launched in 1977. They're still talking to us today, nearly 50 years later.
That's incredible.
And that was with 1970s technology. We're talking 8-track tape recorders for data storage and less computing power than your watch. Imagine what a probe built with robust 2030s technology could do. It could be designed from the ground up for longevity. It could hibernate for decades, wake itself up periodically for check-ins, and use advanced AI for self-repair. It's an engineering challenge, but it's not an unsolvable one.
So it's a time capsule. We launched the absolute best technology of 2035, put it to sleep, and it arrives in the 2080s as this sort of retro-futuristic marvel.
And just think about the arrival. In 2085, the scientists receiving that first signal, that first grainy black and white image of an alien rock, they might be the grandchildren of the scientists who waved goodbye to it at the launch pad. There's a human continuity there that is just quite beautiful to think about.
It totally changes the definition of success for a project. Success isn't, I got the data. Success is, I made sure the data will exist for someone else to get.
Exactly. And you have to consider the alternative. If we say 50 years is too long, what's our other option?
Nothing.
Nothing. We get zero data. 3IAT disappears into the dark forever, and we never, ever know what it was made of. The secrets it carries are lost.
So the choice isn't really wait 50 years or get the data now. The choice is wait 50 years or wait forever.
That's the choice. And let's just quickly compare it to the other big dream, actually flying to another star, like Alpha Centauri.
Right, the Holy Grail.
Even with the wildest, most optimistic propulsion concepts, fusion rockets, laser sails, you name it, a trip to Alpha Centauri is going to take decades, maybe a century. And that's for technology we don't even have a blueprint for yet.
True.
This mission gives us the prize we want, actual physical matter from another star system, without having to travel the 4 light years to get there. We are catching the delivery truck instead of driving all the way to the factory. In that context, 50 years is a blink of an eye. It is, strange as it sounds, the fastest way to touch the stars.
That is a really, really powerful way to frame it. It's a shortcut, even if it takes a lifetime.
It is. And the scientific payoff, I mean, we really can't overstate it.
Okay, let's dig into that payoff. Let's say we do it. The world space agencies get together, they fund this thing, it launches in 2035. Fast forward, it's 2085, the probe wakes up, it's closing in on 3I Atlas. What are we looking for? What is the aha moment that makes the whole 50-year wait worth it?
We are looking for ground truth. Right now, our entire understanding of how planets form, how solar systems evolve, is based on a sample size of 1.
Us. Our solar system.
That's it. We assume that other systems formed in more or less the same way with the same ingredients, but we honestly don't know. It's a huge assumption.
We're just guessing based on what we see around us.
We're making very educated guesses, but they're still guesses. But what if the isotopic ratios of elements like oxygen or carbon are completely alien compared to what we find in our own comets? That would be revolutionary.
What would that tell us?
It would mean the cloud of gas and dust it formed from was different from our own. It could tell us about the star it came from. Maybe it was a different type of star or in a different part of the galaxy. What if we find complex organic molecules, the building blocks of life, that are different from the amino acids we find on meteorites here?
It could tell us if the basic ingredients for life are common throughout the galaxy.
Exactly. Or it could tell us the opposite. It could tell us that our solar system is weirdly special, that we have a unique chemical cocktail that made life here possible. Either answer fundamentally changes our understanding of our place in the universe.
And we can figure this out with instruments on the probe.
Oh, yeah. We can do this with spectrometers, with cameras, with dust analyzers. A key instrument would be a mass spectrometer, which basically weighs molecules and tells you exactly what they're made of. We could literally taste the alien dust.
When you put it like that, it really makes the 50-year wait seem almost trivial. When you're talking about answering the question, are we alone, or at least is our home unique, 50 years is nothing.
It's the kind of knowledge that rewrites every textbook on Earth. And there's another angle here, too, one that Hibbert and his team touch on in their paper. It's the practice.
Practice for what?
Practice for the future. If we as a species ever want to become truly interstellar, if we ever want to send probes to Proxima Centauri and get data back, we need to learn how to do it. We need to learn how to build spacecraft that can reliably last for 50, 75, 100 years. We need to learn how to communicate over those vast distances. This mission is the perfect training ground. It's a necessary stepping stone.
So even if, in the worst-case scenario, the probe gets there and the camera breaks or something, the engineering challenge of just getting it there makes us better. We learn so much along the way.
Precisely. It pushes the boundaries of deep space navigation, long-duration systems, autonomous operations, everything we would need for the next great leap.
I want to go back to the Solar Oberth maneuver for a second because I'm still stuck on the sheer visual of this. Launching in 35, we go onto Jupiter, we U-turn, we dive at the sun. How close to the sun are we really talking here? Are we talking like skimming the surface?
It gets pretty close. To get the maximum Oberth effect, the biggest kick, you want to get as deep into that gravity well as you can possibly survive. The paper models a few trajectories, but we're talking about getting within a few solar radii.
A few times the sun's own radius. That's hot.
It is incredibly, unbelievably intense. The heat shield requirements are significant. You are essentially flying through the outer edges of a nuclear furnace. The radiation environment is brutal. But again, we've done this. The Parker Solar Probe is designed to get even closer than this mission would likely need to. We have the materials. We have these carbon ceramic shields. We know how to survive the heat. The engineering exists.
It's just so counterintuitive. To go to the coldest, darkest place in the void, you first have to go to the hottest, brightest place in our solar system.
Nature loves a paradox.
Yeah.
And the physics doesn't care about our intuition. It only cares about energy. And the most accessible gravitational energy in town is at the sun.
It's fascinating that this proposal is coming out right now in 2026. Do you think there's a new sense of urgency because of how many of these objects we're suddenly finding?
Oh, I think so. Absolutely. When Oumuamua passed through in 2017, it was a complete shock. We were caught totally flat-footed. With Borisov a couple years later, we were a little bit more ready, but it was still fleeting. Now with 3I Atlas, the pattern is established. These things are out there, and they are passing through our cosmic neighborhood all the time.
We just weren't looking properly before. Our telescopes weren't good enough.
Exactly. We are now officially in the era of ISO astronomy, interstellar object astronomy. But I think there's a growing feeling that just looking isn't enough anymore. We want to touch. And the collective frustration of watching 3I Atlas get away is the direct motivation for this kind of innovative, out-of-the-box thinking. People like Hibbert are saying, I'm tired of watching them get away.
It's the scientific hunter instinct. We want to catch the ghost.
And OIATS, the software, is the bloodhound that's finding the scent trail.
Let's play devil's advocate for a moment. What goes wrong? What are the biggest risks, aside from, waiting 50 years and then realizing we forgot to take the lens cap off?
Well, the launch itself is the first hurdle, as always. We need a heavy-lift vehicle to get this thing on its way to Jupiter with enough mass. But by 2035, looking at the trajectory of rockets like Starship and others, that shouldn't be the bottleneck.
Okay, so launch is probably fine.
The real risk, the nail-biting part, is the series of maneuvers. The Jupiter Gravity Assist, and especially the Solar Dive. These are games of incredibly high precision. If you miss your angle at Jupiter by a tiny fraction of a degree, you miss the sun by thousands of miles. If you miss your angle at the sun or your burn timing is off by a second, you either burn up or you miss the target by millions and millions of miles 50 years down the line.
You're essentially threading a needle while riding a roller coaster in the dark.
And you have to do it all autonomously. You can't joystick this from Earth. The light travel time is way too long. The computer on board has to have the perfect clock, has to execute the burn perfectly at the moment of perihelion. It has to be smart and independent.
But again, this is an engineering problem. It's not magic. It's just a very, very hard engineering problem.
It is a solvable engineering problem.
So we have this incredible proposal on the table, a 2035 launch, a 50-year cruise, a dive into the sun, and a rendezvous in the deep dark with a piece of another solar system. What needs to happen now to make this real? This is just a paper, right?
Right now, it's a paper that's been accepted by the Journal of the British Interplanetary Society. It's a proof of concept. To make it real, a major space agency, NASA, ES, maybe a private consortium, or ideally a collaboration of all of them, needs to pick it up. They need to fund what's called a Phase A study.
And that is?
That's where they say, okay, the orbital mechanics math looks good. Now let's get a team of engineers to actually design the hardware. What does the heat shield look like? What kind of rocket motor do we need? What's the power source? They put real numbers and costs to it.
And do you think they will? Is there an appetite for this kind of long-term thinking?
That is the big question. Space agencies are, by their nature, quite risk-averse. They like missions that have a high probability of success and finish within a decade. They like, for political reasons, to have some instant gratification. A 50-year mission is a very hard sell. But But the scientific community is loud on this one. The desire to study an ISO up close is overwhelming. It's at the top of the wish list for a lot of planetary scientists. So I think we might see a real push for this. Maybe not as a huge standalone flagship mission at first, but maybe as part of a dedicated interceptor program.
Maybe a global coalition. This feels like something the whole world should go in on. It's not really an American mission or a European mission. It's a human mission.
It absolutely should be. 3I Atlas doesn't care about national borders. It's a visitor to planet Earth, not to a specific country.
You know, thinking about that 50-year timeline again, it reminds me of planting a tree. You don't plant an oak tree for yourself. You know you'll never sit in its full shade. You plant it for the shade it will give your kids, your grandkids. This mission is a scientific oak tree.
That is the perfect analogy. And in a world that is so relentlessly focused on the now, on the next news cycle, the next tweet, the next quarterly report, there is something profoundly healthy about committing to a half-century project. It forces us to think long-term. It forces us to have faith that there will even be a civilization here in 2085 with scientists ready and waiting to receive the data.
It's an act of profound optimism.
It is. Launching this probe is a statement. It's saying, we believe in the future.
I love that. So here we are, February 16th, 2026. 3I Atlas is speeding away from us at 60 kilometers a second. It thinks it has escaped. But somewhere in a lab, Adam Hibbard and his team are looking at a computer screen, nodding and saying, not so fast.
We're coming for you.
We're coming for you. It's just going to take us a while to get there.
Just a little while.
Before we wrap this up, I want to circle back to the object itself one last time. 3I Atlas. Do we know anything specific about it yet? I mean, from the very brief look we've had so far.
We do. We know that it's volatile rich, which is a fancy way of saying it's acting like a comet. As it got close to the sun, it started outgassing, forming a little coma and a tail. That's actually really good news for a chase mission.
Why is that good news?
Because if it's actively outgassing, it's shedding, it's throwing off particles of dust and gas. That means we don't necessarily have to perform a risky landing or impact on it to sample it. We just have to fly through its tail.
Okay.
We can use something like aerogel collectors, which is what the Stardust mission used to collect particles from a comet's tail back in the 2000s. It makes the catch part of the mission a little bit easier and safer. We don't have to dock with it. We just have to intercept its wake.
Just drive through the smoke.
Exactly. But that cometary nature also adds a layer of mystery. Where did it come from? The trajectory traces back to nowhere specific yet. There's no obvious home star. It's been wandering the Milky Way for millions, maybe billions of years.
A true galactic drifter.
Until it just happened to bump into us.
It really is a ghost. And this plan, the Solar Oberth maneuver, it honestly feels like the kind of thing that belongs in a future history book. You know, in the year 2035, humanity finally decided to reach out and touch the galaxy.
It would be a defining moment. It would be the moment we stopped being just passive observers of the universe through our telescopes and started becoming active participants in the great galactic story.
Well, I, for one, am rooting for it. I might be an old man when the data comes back, or I might not be here at all, but I would absolutely love to see that rocket clear the tower in 2035.
I'll be right there watching with you.
So, to everyone listening, take a look at the night sky tonight. You won't be able to see 3I Atlas with your naked eye. It's already too far and too dim now, but know that it's out there. It's racing away into the dark. But if these brilliant, patient scientists have their way, we haven't seen the last of it. We're just giving it a head start.
A 50-year head start.
Challenge accepted.
Absolutely.
That's all the time we have for this look at the incredible chase for 3I Atlas. It's a story of speed, fire, and an almost unbelievable amount of patience. And it really asks us a pretty profound question, doesn't it? Are we, as a people, willing to start something we know we won't finish just for the sake of knowing what's out there?
I really hope the answer is yes.
Me too! Thanks for listening, everyone. Keep looking up.
And keep thinking big.
We'll catch you on the next one.